David Spears, Civil Engineering Instructor at Texas Tech University, talking about solids, CE 3303. We're in Chapter 12. We're talking about developing the elastic curve for a beam by the use of discontinuity equations. The setup is this cantilevered beam, 9 meters long, with these three loadings on it, 8 kilonewtons per meter distributed load over the first 5 meters of it. And then at this point B, there's a concentrated force couple or moment, concentrated moment of 50 kilonewton meters. At the end we have 12 kilonewton force concentrated load. And we're going to use the discontinuity equations, which are these bracketed equations from table 12.2 in the book. We're going to use the book sign convention in the development of that. Okay, so first I want to draw a free body diagram of my beam, removing the support, replacing it with reaction forces that I then solve for. This is statically determinate, so I can solve for those. The moment at this left end, point A, is this equation here. The moment due to the 8 kilonewton per meter distributed load. Ignore the thing in red right now. The concentrated force couple of 50 kilonewton meters and the 12 kilonewton concentrated force out at the end, 9 meters away from point A. Solving for the moment at A is 258 kilonewton meters, and I can just use sum of forces in the y direction to solve for AY. It's just equal to the opposite of the sum of the loads, 8 kilonewton meters times 5 meters plus 12 is 52 kilonewtons. You can look at example 12.6 in the book for this example. Not as entertaining as me telling you about it though. Okay, as I said, we're going to use the discontinuity equations from 12.2 in the book, and that has 3 columns, one for load, one for shear, and one for moment. We're going to use the equations for moment, which is what we're going to use 99% of the time, because it eliminates some integration. The book kind of shows it with starting off with the load, which means 2 more levels of integration, which I don't want to have to mess with. So I look in that book and on table 12.2, and I see the expression for the moment due to a concentrated moment such as I have at the end of the beam. I have to consider my support reactions as part of the loads on the beam when I'm writing these discontinuity equations. And the formula in the book says a clockwise moment is positive for their equation, which is m angle brackets x minus a closed angle bracket to the 0th power. Now remember, a is the distance along the beam measured from the left. I'm going to measure x from the left end. A is the distance where the load occurs. And so, of course, for this moment and this reaction, the A distance is 0. So that's why I plugged it into this equation, wrote it this way. My moment is counterclockwise, so it's negative 258 times angle bracket x minus 0 to the 0th power. From table 12.2, I also see that a concentrated load, positive is up. The expression looks like this, 52 angle bracket x minus a, but a is 0 because it's occurring at the beginning of the beam, to the first power. Minus, also I have to account for the distributed load starts at a equals 0 or x equals 0. So the expression for the moment created by that, this continuity function, is negative because it's downward, because the sign convention in the book shows upward is positive. Upward loads are positive. It's WO over 2, so it's 8 over 2. Angle bracket x minus 0, a is 0, to the second power. Okay, now I've got all my loads that start at point 0 or occur at point A equals 0. Now I keep going to the right and I come to my 50 kilonewton meter concentrated force couple, and that occurs at a distance 5, or A equals 5, from the left end. And the expression is clockwise is positive, so it's plus 50 times angle bracket x minus 5 to the 0 power. Finally, this is fundamental basic part of these discontinuity equations. If you have a distributed load, it assumes the distributed load runs from wherever you start it, in this case A equals 0, all the way to the end of the beam. So I have to put a counteracting load starting where my distributed load actually ends, there at x or A equals 5, upward on the beam to counteract the load that really doesn't exist, but my discontinuity equation says it does. So I'm going to put this upward acting 8 kilonewton per meter load on the beam for the at the point x equals 5 all the way to the end. So that's the expression for the moment due to it. It's upward, so it's positive 8 divided by 2 bracket x minus 5, 5's where it starts to occur, squared. It runs all the way to the end of the beam. Okay, I could write an equation for 12, but it would be dumb because x is equal to, A is equal to 9, and so it's never going to really enter into my equation because it's just going to be x minus 9. That's the only time it's going to turn on. Remember, these discontinuity equations don't even count. They don't, like what I call turn on, until you reach that point, until x reaches, in this case, 5. Beyond that, or at that point, it becomes the expression x minus 5, just regular brackets. Until then, it goes to 0. We'll see that in here in a second here. Okay, now I'm ready to simplify this out a little bit and let's talk about this. X to the 0 power, anything to the 0 power, is 1. So m is equal to negative 258 times 1 plus 52. X is always greater than 0, or it's equal to 0 or greater. So I eliminate the 0 in the bracket and just write this as 52x. Same thing with the distributed load. 8 over 2 is 4. X minus 0. X is always equal to or greater than 0, so it just becomes 4x squared. Plus the expression due to the concentrated force couple, 50 kilonewton meters. It is 0 at x less than 5. And at x equal to 5, it turns on and it starts to count as a regular bracketed equation. Same thing with the counteracting upward 8 kilonewton per meter load, which is 8 over 2 divided, it makes 4 times x minus 5 bracketed squared. Okay, now I've got a simplified as I can expression for moment. I want to integrate it once to get the slope equation, and then I have to include my EI factor, account for the beam properties. Anyway, EI theta of x is equal to the integration of this thing once. Negative 258 integrates to negative 258x, and so forth. I get 52 over 2 x squared, 4 over 3 x cubed for this expression, plus 50 over 1 x bracketed x minus 5 to the first power. I've just integrated that by 1. Similarly, integrate this once, I get 4/3 bracket x minus 5 to the third power, and then I get a constant of integration. I integrate one more time for the deflection. This is really my elastic curve. That's this expression here. Integrate this once again, and I get negative 258 over 2 x squared plus 26/3 x cubed minus 4 over 3 divided by 4 x to the fourth, and so forth. Get all these expressions. I integrate C1 once, and I get C1x plus C2, my second constant of integration. I kind of simplify it and combine do all the little math, and I get this expression for my elastic curve or my deflection. Okay, now I need to evaluate these constants of integration. The nice thing about the discontinuity equations is I just have one equation, long, albeit, but one equation, so I really only need two boundary conditions. So that's nice. My first boundary condition is that x equals 0, right up here against the support. The slope of the beam, the slope of the elastic curve is 0, and at the support, the deflection, delta, is equal to 0. So I can substitute in x equals 0 into the slope equation that I have right here, and all these terms go to 0. That one's 0, 0, 0. That one's always 0 until x equals 5 anyway. Same with that one. Plus C1, I get all these zeros plus C1, so therefore C1 is equal to 0. Similarly, substitute x is equal to 0 into my elastic curve or my deflection equation, and I get EI delta. Everything goes to 0, 0, 0, 0, 0, plus this is 0, plus C2, so C2 is equal to 0. Therefore, I've pretty quickly gotten to my elastic curve equation. Delta, or the deflection, or the elastic curve, is equal to 1 over EI times this expression, minus 129x squared plus 26/3 x cubed minus x to the fourth over 3 plus 25 x minus 5 squared in brackets plus 1/3 x minus 5 in brackets to the fourth power. Okay, the book didn't do this, but I just want to see what I get for the deflection out at the end of the cantilever, this value right here. At x equals 9, I just plug in 9 to all these expressions, and I get 1 over EI times negative 129, 9 to the 9 squared, plus 26/3, 9 cubed, minus 9 to the fourth over 3, plus 25, and this is the example of evaluating this. Once I've gone past the point of A, which is 5, then I just treat it as a normal bracketed equation. So this is 25 times 9 minus 5, or 4, squared. Similarly, for this final term, I have 1/3 9 minus 5, or 4, to the fourth power. Here's where I've done all the math, evaluated each term, and I get sum of all these is negative 1 over EI, 5,832.6 repeating. And I'm going to have to be careful with my meter, with my units. I've got